Welcome back to Arts Learning. In this video, we'll be going over more types of conservation of energy problems, the ones that really break people down. And we'll be going over how to solve each scenario. So stay tuned. So first, let's go over frictionless ramps. Okay? For frictionless ramps, only height matters. And what do I mean by only height? So you can see over here, right? The block sliding down. You might think that this angle matters, right? Or the friction here matters. But since it's frictionless, we know that the friction isn't consequential here. And theta does nothing. Do you know why? Because energy is a scalar quantity. Okay? Which means it doesn't have direction, which is very unique, unlike force and acceleration and all those vector quantities. Okay? Here, we're just scalar. And what we're going to do is we're going to understand why it doesn't matter. So if we start over here, the block's over here, how much energy do we have? Only potential energy, right? Which is mgh. 3 kgs times 4 meters times 9.8 meter per second squared. And that's going to be equal to what at the end of the ramp? Only kinetic energy, right? Because at the end of the ramp, it hits zero potential. So that means all this potential energy goes to what? Kinetic energy. Or 1/2 3 kg velocity squared. So you see how the mass here cancels? mgh is equal to 1/2 mv squared. The mass is always going to cancel, right? So the mass isn't consequential here. Then you multiply 2gh, then you take the square root of that. So what's the only deciding factor here on your velocity at the end? H, right? Because g is a constant. So that's what you want to remember for frictionless ramps. Now, let's go over how it changes when there's friction on the ramp. Okay? So friction represents itself in two ways. Either sound, right? When you screech really hard, when you brake or stop really hard, you screech, right? And also heat. When you rub something repeatedly across a rough surface, it gets hot, right? Like you rub rocks together and they produce fire. So thermal energy here, this is more of a formal notation, you don't really need to remember that. It's just force of friction times distance, right? Work non-conservative. You could remember Q, but if this is easier, then just use that, because work non-conservative is just easier in general, right? So, it doesn't need to be just this. It could also be force applied times distance, but it's also this, right? So same concept here. So what would this be? This would just be mu, kinetic, times normal, times distance, right? That's your work non-conservative, or friction. So if you replaced it at the start of the equation, so if you remember the equation, plus potential energy initial, blah, 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 is equal to potential energy final, plus, blah, 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 right? Over here, it would be negative if you put it here, and then over here it'd be positive. Why is that? Because we have a loss in energy here, right? Because we have to slow down eventually, which means what's taking away our energy? Friction. That's why we'd put the plus force of friction times d here. Or you could just subtract it at the start, right? So then you understand how these would match up, and the friction would already be accounted for, because you'd have a lower starting energy because of the friction. So then the rest of the energy just goes into the final energy. Okay, so over here it'd be negative force of friction times distance, because you're reducing the initial force to reduce the final force, right? Over here you're just removing from the final force, because the initial force we have, but then we eventually come to a stop, right? So yeah, normal, we remember this from the earlier units, mg cosine theta, ramp friction, mu mg cosine theta. Okay, so pretty solid so far. And on the ramp, you only remember it's mg cosine theta, right? Not mg sine theta. So here, this would be mg sine. Mg cosine as if it was in this way, right? If the block was facing that way. And then here, this would be mg cosine, pushing outwards. So let's try an example, okay? We're sliding down with friction, and we need to know our velocity at the end. So using my equation, work non-conservative plus potential energy initial plus kinetic energy initial plus energy spring initial, which we haven't looked at, but we're going to, okay? We're going to look at that because it's rare, but it does come up, and it's a bit complicated, but it does come up. Okay, so then this is equal to what? Potential energy final plus kinetic energy final plus energy spring final. Work non-conservative is force of friction times distance, which is mu times normal, which I can just replace with mg cosine theta, right? Times distance, right? And if it makes more sense for you, you can put this here, okay? Because that means you have all your final energy, but some of it is going here as well, right? Because the force of friction needs to be accounted for. This is a bit more intuitive than this, so I can just leave that if you want. But applied forces would go here, right? Because you start with initial forces. But friction you can put on either side. So that plus mgh initial, right? Which is what? 4 kgs. Or for right now, actually, let me write all of this in variables, okay? Because sometimes it gets simpler when I do that. So plus mgh, okay? And then kinetic energy we don't have. Spring energy initial, we don't have that either. What is potential energy final? So this side I'll put in green. That we don't have, right? Because we end up at the bottom of the ramp. Kinetic energy final, that we do have. 1/2 mv final squared, right? And then energy spring final we don't. But over here, if I chose to put this over here, I could. Over here it would be negative, okay? So actually, because it makes more sense here, right? Because think about it. All the energy from gravity has to go into kinetic energy, but it eventually stops, right? Because of what? The force of friction and the friction energy, or work non-conservative. So mu times mg cosine theta times distance, right? So what terms can I cancel out here if I'm looking here? Looks like I can cancel out all the masses, right? That's why I did this initially, so I could cancel out a few variables before my work gets complicated. So this is what? 9.8 times h. So we have a 30-degree angle here, okay? Which means this has to be 3 meters. Or, okay, so this is something you need to keep in mind, okay? If you're given just the length, which is 6 meters, how would you find this height? Well, if you think about it as a vector, right, it just sits times sine of 30. That's the height, right? Sine of 30 is equal to x over sits, because opposite over hypotenuse. And sits sine 30 is just your opposite side. So sits sine 30, I mean, over here you can see 3 meters, but in the question we're just given L is equal to 6 meters, right? And I'm going to ignore my units for now, which is dangerous, but it's just going to get a bit complicated, right? So I'm going to remove all of this here, so we have more space. Okay, yeah. Now let's go at it. So this times what? Well, that's it, right? GH is equal to 1/2 velocity final squared is what we're trying to find, plus mu, which is 0.2, times g, 9.8 times cosine theta, which is what? 30, right? 30 degrees times d, which is 6 meters, right? It travels the entire length of the ramp. So that's what you want to keep in mind, right? That's not going to be 3 because 3 is the height. What's the distance it travels? It falls down the ramp. So 6 meters. Okay. So this is very, it can get very complex very quick, right? Maybe not complex as in conceptually, but you see how many terms I had to write out for just the friction itself, right? So this, I mean, and if you used your mass as well, if I canceled out the masses at the start, but if you use those, it could get even more complicated, right? So always remember to try and simplify it down and always keep track of what's happening, okay? If you miss even one number, it's all over. I mean, the question's all over. I don't want to sound dramatic, but you're probably going to get the question wrong. There's no flukes. So over here, this would be 9.8 times 3, right? Or just 29.4 is equal to 1/2 v final squared plus 0.2 times 9.8 times cosine 30 times 6, or 10.18. So I subtract that from 29.4, right? Which leaves me with 19.22 is equal to 1/2 v final squared. I multiply both these sides by 2, and I get 38.44 is equal to v final squared, which means v final is just 38.44 square root, which is 6.2 meters per second. All right. Now what are we going to do? We're going to look at moving upwards. So imagine a ramp, but here what's happening is you're moving up the ramp. Okay, so you start here, but you're going upwards. So what are you going to initially start with? You could be pushed, right, which gives you a force applied, but here we don't have that. So we're just going to assume we have what? How are we even going to travel up here? Kinetic energy, right? So potential energy initial, we don't have that. Work non-conservative, we do have that. Kinetic energy initial, we do have that. Energy spring initial, we don't have that. Is equal to potential energy final plus kinetic energy final. We know that's just going to be 0. Why do we know that's going to be 0? Because that's going to be the point where it stops, right? We want to know how far it can travel, which is how far it travels with the kinetic energy before it stops, which means it has its maximum distance, right? Maximum potential energy, and then it just falls back down, okay? So energy spring final, don't have that either. So this is going to be kinetic energy initial, which is, so a bit messy here, but let's work through it. 1/2 mv initial squared, right? M is 2 kgs. Actually, let me write it out because I could also cancel out some terms, right? Could save me some time. 1/2 mi initial squared plus work non-conservative. So I could do that right here, or I could do it over here. So we'll see what I'm going to do first. Potential energy final. So think about it. The block has to slide up the ramp till over here, and that's its maximum point, right? That's when all the potential energy is going to equal all the initial energy, because then that's when it's going to stop. It's going to have 0 kinetic energy, and then it's going to stop, right? So what's that point going to be? Potential energy final is just mgh. But the thing is, we don't have an h, right? Do we have an h? Not really, right? So how are we going to deal with that? What we're going to do is we're going to do you're going to use d, which is what? This is theta here, but d, so if I erase this for a better picture, right? So we know that, let me just rewrite this to be potential energy final, because we know that. And then over here, if I do this, the ramp's distance would be d, right? How would you find the height from a d if you knew the theta? Sine theta is equal to height over d. So d sine theta is just h. So in this case, we're given theta is what? 25 degrees, right? So d sine 25 degrees is height. So we can just plug that in over here. mg d sine 25 is plus, so if you use force of friction here, because you have kinetic energy initial, right? And then what happens? It's slowly withered away by the upwards movement, by the friction of the ramp, okay? That's why it can go even further, but because of friction, it goes a slower distance. It goes a lesser distance, right? So if I added a force of friction times d here, then the initial energy would be distributed among these two, which makes this lesser, right? You can just think about it like that. Because the final, you had the force friction times d as well, which is what? Mu mg cosine theta times d, right? So if I erase this, what can we do here? We can divide all the m's out, and then we can start substituting, right? Before we do that, let's just see if there's something we can simplify further. Okay. So if you look at the equation here that we have, do we know our velocity initial? We know that, right? 10 meters per second. We know our velocity final was 0. That's why we cancel out that. So 1/2 velocity initial squared. And then we have to find a way to get d from this, right? How can I get d from this? I can just factor it out of this expression. D times g sine 25 from over here, right? This is g sine 25. If I factor the d out, it's going to be d times g sine 25, right? Which gives me the same value. Plus what? Mu times g cosine theta. Or I can just write 25 here. But I just factored out the d from both these terms, right? So what was I left with then? I was just left with this. So I can just divide the entire thing by this expression, this massive expression here, right? So it's just going to be velocity initial squared over 2 times 9.8 times sine of 25 plus mu, which is 0.15 times 9.8 times cosine of 25. So these problems get very tricky very fast. Velocity initial here is 10 squared. So 100 divided by 2 times 9.8. Okay, so actually, yeah, let me do the denominator by itself first. 9.8 times sine 25 plus 0.15 times 9.8 times cosine 25, which would give me 5.47-ish. You multiply that by 2, and then you divide 100 by that, which would give me something around 9.13 meters. So not too hard, right? But there's a harder version of this problem. When you have two ground surfaces and you have friction here, but that's a different coefficient, and you have friction here as well. That's a real hassle, right? But if you look at those later. And then the other type of question you could have is friction given as a force. So a biker is going down a 5-degree ramp, right? So he starts here. He's going downwards. Angle here is 5 degrees, so probably not to scale, right? 5 degrees would be way smaller, but it is what it is. And friction is 60 newtons. Okay. So, how do we find out our velocity as well as our mu from this? Okay. So, a 90 kg biker. Okay, we're given some other details as well. So that's not just it, right? He's 90 kgs. He starts at rest and 5 degrees from horizontal here. 500 meters long is the ramp length. So D is 500 meters. So initially, what does he have? Potential energy, right? Because he's starting from the ramp. He doesn't have any kinetic energy. So initially, potential energy, what is going to look like? 90 kgs times 9.8 times height, which is 500 times sine 5, right? Because the height is here, distance is here, so, right? So you have to do sine of this times 500 to get height. And then that is equal to what? So plus no spring, no kinetic. So that's it by itself then. And over here we have 1/2 mv squared. So 90 kgs times velocity final squared plus what? No potential energy because we're going to be at the end of the ramp and our height is 0, mg 0 is just 0. No spring for the same reason. But what about friction? We have that, right? You remember when I told you that you can either put friction as positive here or you can put it negatives here, because this force that we have at the start, it's getting distributed into two energies, right? I mean, this energy here is getting distributed into two energies. This energy, which is kinetic, and the energy of friction or heat. So what's that going to look like? Force of friction, which is mu. Or, I mean, we have the force of friction right here, right? So I'm not going to do all that calculation. The 60 newtons times D, which is 500 meters. So this should give you 90 times 9.8 times 500 times sine 5. So a lot of words, right? Subtract that from that 60 times 500. Multiply that by 2. Divide that by 90. And then take the square root of that, which would give you around 13.69 meter per second, which you can round up to 13.7, but I'll keep it at 2 decimal places for now. Okay. And what if you needed to find mu? Well, we know the force of friction here, right, is mg cosine theta. So I was just contemplating whether to say mu or m first, but since I went with m, I'll just say that, times mu, right? So mu times, what is mg cosine theta? Mass is 90. Gravity, acceleration due to gravity is 9.8. Because gravity is not a quantity we can measure, right? It's acceleration due to gravity. Times cosine of 5 is equal to 60 newtons. Because we're given that, right? So 60 divided by 9.8 divided by 90 divided by cosine of 5. And our coefficient of friction comes out to be mu is equal to 0.068. Okay? So we had two unknowns there, but we were still able to solve it, right? So that's just a testimonial to the fact that you can solve energy equations without all the values. Sometimes you can even cancel out the values, okay? Because you might be given all these masses here. You might not even be given the mass, and people will start asking you, wait, we need the mass. How are we supposed to solve this problem? You can cancel the mass out, right? Just like, so in this scenario, I didn't do that. I just went directly to plugging and chugging, but usually I'd probably cancel out the mass. Okay? So now let's go over turning height into force. You're pushing a 1 kg ball up a frictionless ramp. Okay. 1 kg. No friction, so forget about that mess. Its weight is 10 newtons. So that means that, weight is just force times force of gravity, right? Which is just mg. So we're using 10 meter per second here, but usually I'd use 9.8, right? They're similar, but I would usually use 9.8. So then what would I do? Push that steady speed up a frictionless 5 meter ramp to a height of 3 meters. Find the work done and the force needed along the ramp. So if it's pushed, how far is it pushed? To 5 meters, right? To a height of 3 meters, which means over here would be 3 meters. I don't know why I put it over there. And then if you know Pythagorean triple, this should be 4 meters, right? Using the 3, 4, 5 Pythagorean triple. Or you could just use the Pythagorean theorem, but this is more easier, right? So work, if you remember, was force times distance. And what's the force here? Pushing us down? 10 newtons. Right? And you multiply that by the height it's pushed up, which is 3 meters. So you get 30 joules of work that you've done. And then what? Force is work over distance, right? So you could just find the actual force you did, which means, so how do I say this? The ball's work, the work done on the ball here, it went up 3 meters, right? So the force of gravity, what's the force of gravity? The force of gravity is also doing work on the ball, right? But that force is getting rejected because you're moving it up the ramp. So the ball here gained 30 joules of energy, which means you must have been pushing it with 30 joules of energy, right? So if you're pushing it with 30 joules of energy, because you gave it 30 joules of energy over here. So if it has 30 joules, then what lost 30 joules? You, right? Energy transfer, conservation of energy. You're not going to give it something without it taking back from you. So it's a bit complicated where that energy comes from, but it's like chemical energy from your food. You ate something, and then that's giving you energy to push this. So 30 joules is equal to 10 newtons. Or in this case, we don't know the force, right? We're looking for the force, because it's the force applied that I'm using to push it. So misstep there, slight misstep, times distance, which is 5 meters along the ramp. So the force I apply is 6 newtons, and the work is 30 joules. Since the ball gained 30 joules, I must have pushed it with 30 joules, right? And then since I pushed it with 30 joules, I pushed it across a distance of 5 newtons, so I can find the force I did. The ball won't gain energy from nowhere, right? It has to gain it from me. Okay, so now let's go over how to solve for a ramp angle. So we have to find the angle from the final speed. Okay, a 2 kg block slides from rest down a frictionless ramp 4 meter long. So probably looks like this, right? Because the block is sliding downwards. And reaches 6 meter per second at the bottom. So velocity final is 6 meter per second. And we need to find the ramp angle. So not a lot given here, but again, we don't need a lot, right? Because friction thank God, isn't existing here. So we can just write our equation again. What do we have here? What's our, energy initial? So we have no spring, no kinetic. What do we have? Potential energy initial, which is the block's mass, 2 kgs. Or I'm actually just gonna, because before I wasn't being as efficient with just writing the variables, so I could just do that here. mgh is equal to, what is this? Kinetic energy, right? Because at the end we have 0 height, which means no potential energy. So 1/2 mv squared. V final squared, or just V final squared, yeah. So at first glance you might be like, where am I getting the data from here? This doesn't make sense, right? But what are you going to substitute in for height? So if you want to find the equations, you'd probably cancel out the masses. Then you do velocity final squared is equal to 2gh. Then you take the square root of that, right? But you don't have the height here. How can we represent the height given this? This is d, right? This is the hypotenuse. And if you have a theta, you have an opposite and you have a d, or hypotenuse. Sine of theta is equal to opposite over hypotenuse. So your opposite value, which is your height here, so a bit confusing because there's 2 h's, but I'll write this as height instead of hypotenuse. I'll write this as hip, is equal to hypotenuse, or just d, times sine theta, because d is the distance I traveled, right? Which is the hypotenuse along the ramp. So this would just be square root of 2 times 9.8 times d sine theta, which is what? 4 meters times sine of theta. And we can just plug in for velocity final because we know what that is, right? We're given that. We need to find the angle here, not velocity final, even though the equation looks a bit differently sorted for that, right? So here we're given 6 meters per second squared. But since I square root it here, it just be 6. So how can I solve for that? Whoops, calculator. You can square 6 on both sides, right? So you'll get 36 here is equal to 2 times 9.8 times 4 times sine theta. So you divide 36 by 2 divided by 9.8 divided by 4, and then you take the arc sine of that, which should give you 27.3 degrees. So these are some problems I won't go over, right? Because I just did go over all types of these problems that can be hit with. But feel free to just try them out on your own. That's why I'm leaving it open right now. Okay? And those were only some of the hardest type of problems you can encounter, okay? Like I was saying, what if you have 2 friction coefficients, or you start somewhere and end somewhere else, or you have a pulley and you have a ramp and you have crazy stuff, right? Don't worry, I'll make sure you understand all of them. I'll make sure you know how to do all of them. Okay, so keep following my channel, give me a subscribe and a like so I can help others and keep you updated on physics.